Right. Hi. Hello. For chapter two, we're just gonna go over some levers and how the body is in relation to that. The mechanical advantage of those bodily levers. How exertion during those specific joint movements, and then we're just gonna go from some calculations of some real world athletic examples. So yes, that's about it. um, right, for first class levers, the fulcrum is in the middle. Um, think of think of your neck, think of your head tilting back. You have just a simple lever right there. For second class levers, think of the resistance being in the middle. Uh, Examples, think of just you standing on your toes doing a calf raise, right? You have that simple flexion, and it kind of just creates a second class lever. For third class levers, think of how the force is in the middle of the lever itself. For example, think of a bicep curl, how you have lots of concentration within that specific area. So, yeah, the mechanical advantages of first class levers, they could change. It changes depending on its position. For second class levers, they have just greater mechanical advantage. For third class levers, they have the least mechanical advantage, but they allow faster movements, and how those kind of relay to the body. Most human joints use third class levers. Like I said, they allow faster movements and larger movements, greater in scale. Even though for those levers, like I said, since it's less mechanically advantaged, you're gonna have to need some muscle to actually back it up. It wouldn't be as effective if that were the case, but that that is. So some positions, um, yes, it would just need more muscle force for those third class levers. For changing exertion during joint movement, the force the force needed need the force how do I phrase this? The force needed changes during movement because these joint angles, and just everywhere's a joint angle, um, it affects it complements with that muscle advantage. It has an effect because of that. So some positions require more effort from the muscle side of things to help back up the actual joint angle movement to begin with. Right. So now we go to some good calculations and the more scientific base side of, I guess, these joint angles and energy as well, that is needed, which is going to be done under almost three main things. So we're going to have to deal with force, work, and power. These three things are essential for these calculations. So we're going to differentiate between a deadlift and a snatch, and the meters per second, and the amount of energy that is needed, measured, I believe, in watts. Yes. So stay tuned because that's very fun. Right. So deadlift. Think of 150 kilograms. right? So that is the weight. I told you we also need the distance. The distance, 0.30 meters, and the time is 2.5 seconds, right? So what you have to do is you get the force and you multiply that by the 9.81, which will give you the 1471.5 newtons. And then you're also going to have to deal with the work. So you're just going to have what you just calculated, the 1471, and then by, which is the distance. So the work, or what we have is the 1471.5 multiplied by the distance, which will definitely decrease that number since you have a 0.3. So the new number in joules will be 441.45. So then once you have that number, you can now calculate the power, which can be converted into watts. So you're going to have what we just used is just the 441.45 divided by 2.5. The 2.5 is the time, 2.5 seconds. So then you just calculate that, which will equal 177 watts. So the deadlift power when you just pull back, deadlift power generated that is needed is the 177 watts. So once you have that, you can now focus on the velocity. So with the velocity, think the deadlift power, the 177 watts, that's what you have. That's great. For the velocity, it's just the distance, divided by the time. So how much meters per second to actually get that raised, or to generate to get that raised. So you would just do the distance, which is the 0.3 meters, divided by the time, which is the 2.5. So the 0.3 divided by the 2.5, which will get you the 0.2 meters per second. Now with the snatch, or let's rewind a little bit. With the deadlift, you're not gonna exert as much energy as you would need, how much power you would need, versus a snatch where you're bringing a very explosive movement into the mix, which will just require a lot more energy in watts to be able to function properly for the snatch. So for the snatch, if it is 75 kilograms compared to the deadlift, which I believe was 150, we said, there's definitely a shift in weight. So keep that in mind. So with the weight being 75 kilograms and the distance being 2 meters versus I believe we did, right, which is different from the 0.3 meters. This is starting at 2 meters, or what you got to get. And then the time is 0.5, which makes sense. It's a more explosive movement. So the force, what we said was how much the weight of it was, which was 75 kilograms. So just do the 75 by 9.81, which would get us 735.75, and then you would plug that in to the work formula. So work, which you already have from the force, because that's what you need. It's just the force and the distance. So you would put the 735.75 times 2. Remember, 2 is the distance, so it's just the beginning of the force and the distance, which will get you 1,471 newtons. Joules. Sorry. And then from there, we are now focusing on the power. So it's really great how this works too, because you could from the force to the work to the power kind of just go down the line. so it's a little easier to maintain and remember. But for the power, it is 1471.5 divided by the 0.5. So remember, we have what is left from the work in the joules and what is the time. So you just do the 1471.5 divided by the 0.5, which will get you your power in watts, the 2943. So once you get that calculation right there, you can now that's what the snatch power is, which is significantly more than the deadlift, because the deadlift was 177, which makes sense for that to be 177 versus the energy needed. Keep in mind, think of power as well as time as well as distance. They all contribute to the matter itself. So this makes sense for the snatch movement, to have a more explosive effect, more energy required. And just going back to the levers, more not only the joints themselves and the skeletal system itself, but as well as the muscles behind it to actually physically generate that energy to complete your lift properly. So yeah. So then once you have we're done with the snatch power in watts, which is the 2,943. Velocity's rather simple to get if you're given what everything is, because remember, we started off with the weight being 75 kilograms, the distance is 2 meters, and the time is 0.5 seconds. But really, for velocity, you would just need the distance divided by the time, which would get you 4 meters per second, which is also significantly better than what do we say, the 0.12 for the deadlift. And like I said, everything checks out, because if obviously it also depends on the weight. I think that's one of the main things too. For the deadlift, you're gonna have a good amount of weight, so it's hard to generate a quick explosive power with that, just being as the exercise is, versus, like I said, the snatch, where you can really give it your all to exert much more energy and effort, whether it be just the lighter weight or just everything involved with lifting that up. So going back to the movement velocity, there's a significant shift, with the deadlift being 0.12 meters per second, which is a slower movement, and the snatch, which is 4 meters per second, which is a faster movement. So the snatch has higher power, it generates higher power. It takes more energy to do that, because the weight moves faster, and then over just that greater distance, because a deadlift, once it's off the ground, or once you get it up past a certain point, that's it. But to have a snatch, for example, it's going so much higher than deadlift. So the snatch would most definitely have higher power, because of that weight being lifted over a greater distance, as I said. I think that's it. I'm sorry if that was really confusing. I have everything calculated. But yes, that's all. Okay.